So I want to talk about today is a distributed source coding problem with two Gaussian sources, with a joint Gaussian sources, and I want to show that the achievable weight region for this problem is given by this basically intersection of these three weight regions here. Okay, the background of this problem is basically you have the source, and we are going to compress that with an encoder, and with certain rate here, so bit per samples, and then we are trying to reconstruct that at the decoder, and it's distributed in the sense that encoding are separate, but decoding is joined. So we have the recover x1 and x2 are corresponding x1 hat and x2 hat, and we have a target distortion. Basically, we hope that the distortion, expected distortion, to be less than equal to d1, and expected distortion is less than for d2, x2 is less than d2. And we say it's achievable. It's basically for the weight pair to be achievable. Basically means that we can find encoder and decoder pair such that this distortion is satisfied. So the achievable weight region are basically derived from the Bergerton inner bound. Basically, the Bergerton inner bound is just a very much intuitive scheme. Basically, the two encoder, instead of trying to compress the source x1 and x2 directly, it will look for a kind of auxiliary random variable u1 and u2, and so basically, okay, actually I probably will give another presentation about Bergerton inner bound, but here I will just give the expression here. So eventually the bound will be R1 and R2 is bigger than equal to this, the conditional visual information between U1 and X1 given U2, and the corresponding R2 is the visual information between U2 and X2 given U1, and the combined weight has to be less than the visual information between U1, U2, and X1, X2. And also, because this U1 is generally only based on X1 and U2 only generally based on X2, we have a long Markov chain here like U1, X1, X2, U2. Okay, that's just a Bergerton inner bound. If I have chance, I will give another presentation on that. And I want to, okay, again, the region, the final proof, the regions is given by this R1, R2, and RS here, basically combine this intersection of these three regions here. Actually, as you may guess, basically, this R1, R2, and RS is basically just corresponding to these three kind of inequality in the Bergerton inner bound, kind of, but not exactly, because if you look at, for example, the first weight region, we have R1 is bigger than something like a function of R2 here, but in the Bergerton inner bound, actually this is just a constant there. So we'll see why it's so. So before we get into how to show that this is achievable, let's study a little bit the weight regions here. So the weight regions can be plotted like this. Actually, the regions will depend, the shape of the region, I should say, will depend on the distortion, the target distortions, D1 and D2, and also the correlation role. So basically, the correlation is the is the correlation coefficient between x1 and x2, in the sense that we basically we are assuming x1 and x2 is just joint Gaussian with zero mean and a covariance matrix 1 row 1. So in the sense we are actually assuming x1 x2 to have a same variance of 1. It's okay to do that because it's quite easy to show that for other case we can always scale the source to have the same variance as this one. Have to have unit variance, so we can just consider this special case here. Now for this special case, we actually depends on a combination. Also one more thing, without loss of generality, we just assume D2 is bigger than or equal to D1. This makes it a little bit simpler. We have only a couple cases. Oh, by the way, this whole presentation is based on the proof by Kim and Gamal, or the textbook by Kim and Gamal. I think it's called Lateral Information Theory. So it's a rather new textbook. It's just a couple of years ago. So I guess 3 years ago, 4 maybe. So okay, yeah. So if I have like 1 minus D2 is bigger than this guy here, then I will have actually this R D1 and will have like intersection like that. If I have this is exactly equal, then I will have this three boundary of the regions can overlap at the point here. This point here, I think is a 1 over 2 log 1 over D1, something like that. So okay, actually this line here I want to say is the boundary of RD1, and this is the boundary of RS D1 D2, and this boundary RD2. So okay, we will show that this is indeed the case. So basically, let's see. Yeah, we have RD1 is given by this, and actually therefore we can also rewrite this as R2 is bigger than this. So actually we just kind of flip the condition here. So instead of having R2 as the dummy variable, we have R1 as the dummy variable. And if we write it this way, then we can see that the R1 region, the boundary of R1 region will intersect the axis at 1/2 log 1 over D1 M0, and intersect as 1/2 log rho square D1 plus rho square minus 1. That's this case here. I have set basically I said out. Okay, basically what I did is I said R2 to be 0 for this one, and I said R1 to be 0 for this one. And similarly, I will have the intersection for R2, the boundary of R2 at these 2 points here. And so if we just compare the intersection point at the x-axis, then for R1, I have 1/2 log 1 over D1, and R2, I have this one here, rho square over D2 plus rho square minus 1. And RS D1 D2 is given by this guy here, actually. Here, I guess. Too far away. Yeah, it's given by this one here. And by the way, the beta is kind of complicated. It's this guy here. Now, if I want to see like when this kind of crossover out, when will be like this is less than this or bigger than this, Then I compare these two terms here with a little bit algebra. I found that like 1 over d1 will be equal to whole square d2 plus whole square minus 1 if I have whole square 1 minus d1 is equal to 1 minus d2. That's basically the condition here. That's the condition here. Then this R1, RD1 and RD2 will overlap. If I have either this 1 minus d2 is less than equal to this side here, I will have now this RD1 move to the left, right. And if I have the other way around, I have this RD1 move to the left. So for that case, I will have like this, actually this three overlap here, then I will have the intersection of the region that will correspond to here, right? So if I have this case here, the intersection of the region is just this here. And actually, if we derive, we do some algebra again for our S d1 d2, compare rs d1 d2 and r1, we find that the condition is the same. Actually, it's a little bit complicated, but it's still the same. So we argue that when because if we look at the intersection point here, like with the x-axis, then when we have this 1 minus d2 is less than whole square 1 minus d1, then we expect that like rd1 will be on the right hand side of like rd2 and or like something like this is inside rd2, r2d2 I should say, and also rs d1 d2. But of course, like this is, if we just argue that based on the x-axis, it's also possible that like this r1 d1, the boundary actually cross over the boundary of r2 d2, or like cross over the boundary of rs d1 d2. But we can actually show that like r1 d1 is indeed inside r2 d2 and also rs d1 d2. So let's just start with like r1 d1 should be inside rs d1 d2 when this condition 1 minus d square is less than equal to whole square 1 minus d1. So actually this is kind of like a repeat of like what we talked about earlier about the where is that? The derivation here, we skip some step here. That is, under what situation rs d1 d2 will be kind of like at the point like and r2 equal to 0. The r1 will be for this region. The r1, the boundary of r1, the boundary of rs will be bigger than r1. So, or like we want to see like when these two will overlap, right? Basically, that's when this guy here, maybe I change it a little bit for the moment. So these three expressions are corresponding to the to r1 at this point here, and also at this point here, and at this point here. So we want to see when this r1 d1 will intersect with will overlap with this rs d1 d2. So in other words, this one is equal to this one. So this happen. Basically, I can just equate that, and so that means that we want this guy is equal to 1. Then okay, this beta here is actually equal to this guy here. It's a little bit ugly, but again, do some algebra. I just multiply 2d2 here, then move the terms to this side, and then we can square it on both sides, and then I just cancel some term. We get d2 is equal to this guy here. So at the point when these two overlap, let's call this distortion, required distortion, target distortion, d2 pi here, it will be like equal to 1 minus rho square plus rho square d1. Now if we consider the d2 is actually bigger than equal to this d2 pi, or bigger than equal to this guy here, or this condition is satisfied, then if we consider any point inside the wave region of R1 D1, then that wave region will be bigger than equal to this one plus this one, right? Because I have this R1 has to be bigger than equal to this. So these two sum together, I can merge the terms together to get this, something like that. So what need to be realized is that like if we consider R2 is equal to 0, then okay, this will be gone. Then I will just have like 1 minus rho square plus rho square. I get rho square got cancelled. So I will just have like 1/2 log 1 over d1. And also we can see that like this function is actually an increasing function, right? Because as R2 in 1 minus rho square is bigger than equal to 0, so as R2 increase, this thing increase, and so that whole thing increase. So therefore, like this has to be bigger than equal to log 1/2 log 1 over d1. And so therefore, like this thing should be set. And okay, I guess I missed a little bit thing here. Oh, here I missed this thing here. Actually, we went through that, but I didn't emphasize that. So when for this to be equal, then what's going on is also the bound now will become 1/2 log 1 over d1, right? So therefore our SD1 d2 pi is actually equal to this thing here. So therefore, because we show that like R1 plus R2 is bigger than equal to 1/2 log 1 over d1, so for that particular R1 and R2, the R1 and R2 is actually inside R1 d1 will also be inside our SD1 d2 pi. And of course, like, because d2 is smaller than d2 pi, sorry, it's smaller or bigger, I forgot. Sorry, d2 is bigger than equal to d2 pi, and that means that like you have a looser constraint. Because the constraint is less, then the weight region you expect will be bigger, right? Because now the constraint is looser, there will be more weight to be achievable. So therefore this will be inside like our SD1 d2, so that we prove that part here. Let me take my break first. Okay, now let's show that like R1 d1 will be also inside R2 d2 when the same condition is satisfied. So we can just recall that like R2 d2 is given by that, or we can rewrite that, just flip the condition here. Instead of R1 is kind of like a dummy variable, we have R2 as a dummy variable, we have R1 will be bigger than equal to this guy here. And then so when we have this condition satisfied, it means that d2 is, we can rewrite that d2 is bigger than equal to this guy here, or we can write D1 is less than equal to this guy here. Now for any point in R1 D1, we will have R1 has to be bigger than equal to that. That's the condition for a point to be R1 D1, and it will be bigger than equal to this here. Here we just use the condition here, because D1 is less than equal to that. We can substitute this. Now have a bigger terms here in the denominator, so therefore this term will be smaller. And this we can show that is bigger than equal to that, and this is actually the condition for a point out, weight pair to be the region D2, right? As long as R1 is bigger than equal to this term here. Now for this, why this is bigger than equal to this guy, basically we can just show like this fraction is bigger than that. We can just, so it'll be like something like this whole square, something this 2 plus whole square plus minus 1 whole square is bigger than equal to that. We want to show that, so this is kind of equivalent to this guy multiplied by this guy, right? Minus this guy multiplied by this guy is bigger than equal to 0. So we call this F out here. And if we look at this function here, this multiplied by this minus this multiplied by this again, what we find is that we have a bunch of terms. The rest of the term is actually independent of R, and there's only a couple terms depends on R, and we can summarize those terms into something like this. And again, what we can see is that for those terms, as R increases, this whole function fr will increase because this term, as R increase, these terms will get bigger. As R increase, this term will get smaller, but I have negative sign, therefore this will get bigger also. So, and also again, so therefore I will have fr is bigger than f0 here. But of course, if we look at f0 is equal to 0, because that if substitute 0 here, this will get this term here is actually equal to this term. Therefore, this multiplied by this is equal to this multiplied by this. Okay, therefore, we show this thing here. So we have what we just show now is basically, if we have this condition is satisfied, then this weight region will be basically R1D1 will be inside the both other regions. So therefore we can just consider this weight region here, as long as we can show that every weight pair in these weight regions can be satisfied. Then we can show that the intersection of these weight regions are achievable, right? At least for this particular case here. Now, so let's get back to the Birketon scheme. We call that the Birketon scheme basically is composed of something like that. We basically have the encoders to utilize some auxiliary random variables u1 and u2. such that the U1 and U2 should satisfy the long Markov chain, because U1 only depends on X1 but not on X2 in X2 and so on. And this Markov chain will be satisfied if V is independent. Basically, V is a vector variables composed of V1 and V2. I shouldn't say V is independent. I mean, the elements of V are independent. V1 is independent of V2. And if V1 is independent of V2, that just means that the covariance matrix of V as a vector form is just a diagonal matrix. So I have, like, let's say, the variance corresponding is M1 and M2. Now, if we compute the conditional probability Px given U, I can write this. Basically, this is a posterior probability. If you think of like U is an observation, X is what you want to estimate. It's proportional to the likelihood multiplied by the prior. And it is also proportional to this thing here, because X itself has a distribution. It's a zero mean with covariance is 1 rho 1, and Pu given X is basically has mean. Actually, this is not even proportional. This is actually equal. Is equal have the PDF is basically is have mean X and has the covariance is sigma VB. That's this one here. And of course, like this PDF here, this is just actually a Gaussian PDF. Actually has a form like this, and you can see that X and mu is actually is kind of is commute. You can swap X and mu and doesn't change anything. So therefore, this is also equal to n x mu sigma VB. And now if you look at this here, it's basically just multiple of two Gaussian PDF. If you do some complete square method techniques, then eventually you will derive something like this. Actually, this is pretty simple, but it's a little bit tedious. This will become a X with mean like this and with a covariance like this. Actually, another way to think of this is really you are having two observations here. One observation is like with mean mu, the other observation is mean 0, and have like one observation with covariance sigma VB, another observation with sigma X6. And with these two observations, they are independent. Then the combined PDF will be just a multiple of that. And then you can think of like the final estimate will have a mean, basically is a weighted sum of the mu and also 0. Actually, there's a no 0 term here because weight that 0 multiplied by weight is just equal to 0. And the covariance is just equal to the sum of the inverse of the sum of inverse of covariance. It's kind of mouthful, but actually this inverse of covariance, there's another name for that, is just the precision matrix. And if you think of the precision matrix, then this thing is very much intuitive and reasonable, because we have essentially just saying that if you have two observations, then the precision matrix of the final observation, taking account of both observations, will be the precision matrix of taking one observation plus the precision matrix of taking another observation. And as you have larger precision matrix just means that you are able to get better estimation. Therefore, this is very reasonable. Okay, now with this precision matrix formula, I can compute this sigma x given u, and actually, let me write it in a form like this, because this is actually correspond to the final distortion, right? So the diagonal element is basically just the variance of your estimate at the decoder, and of course, because the source itself is zero mean, the variance of that estimate is just equal to distortion. So we can write, since we know that the target distortion is D1 and D2, we can write the form as a diagonal D1 and D2, and the off diagonal will be just the theta times the square root of D1 and D2 if we assume theta is the correlation coefficient between the two variables. And then sigma VV is basically sigma VV because it's diagonal, so therefore the inverse is just equal 1 over n1 and 1 over n2. It's also a diagonal matrix. Then we can substitute everything into here. And we know how to find the inverse. It's pretty simple for a 2 by 2 matrix. And if we look at the off-diagonal term here, because this sigma VV inverse does not have its diagonal, does not have an off-diagonal term. So if we just compare the off-diagonal terms, it actually does not depend on n1 and n2. Therefore, we can get something like that. And using that, we can try to solve for theta. And that will only depend on rho and D1 and D2, but not on n1 and n2. So basically, we just do a simple algebra and we arrange the terms. Then we have we can write write this equation into a quadratic equations of theta. Then we can solve theta, and because it's a quadratic equation, it have two solutions. Like I have plus sign here and also minus sign here. But if you look at it more carefully, this thing is positive. 1 minus rho square is positive. And square root of this guy here is just equal to this guy here. Therefore, this thing, the magnitude itself must be bigger than this thing here. So, therefore, if I have minus this thing, minus this, and again this is positive, the whole thing, in terms of magnitude, must be bigger than this thing here. So, therefore, like, when we take the minus sign, we actually will have theta have a magnitude bigger than 1. But of course, theta is a correlation coefficient. It has to be bounded. I mean, the absolute value of theta has to be bounded by 1, less than or equal to 1, and therefore, like, we can only take the positive sign solution. So I have theta is equal to this. Now we can substitute theta back to compute this sigma x given u, and that's some algebras here, just rearrange terms, blah blah blah, and eventually we will get this. And this is exactly what we have to specify the weight region for our SD1, D2. So therefore we have R1, R2, or R1 plus R2 bigger than or equal to that, and we compute this one. Okay, by the way, actually, just a reminder how we get this to here. This I U1 U2 given x1, given x1 x2 is equal to the entropy of x1 x2 minus the conditional entropy of x1 x2 given U1 U2. Or like we can write the vector form is x and u here. Hx given u is just 1/2 log 2 pi e. This is a determinant 2 pi e of sigma x given u. And similarly, I have this is 1/2 log 2 pi e x, and the determinant of that, or sigma x determinant of that. So, and because log something minus log something is just equal to log something over something, so it's 1/2 log the 2 by u will got cancelled, so it's sigma x over sigma x given u. So we have that. And then we know sigma x, the determinant of sigma x, we know determinant of this. We substitute everything, we get that. And as I said, like this is the bound we have that we define the weight region for our S D1, D2. This is PT here. Let's evaluate the distortion in terms of M1 and M2. We call the sigma xx is this thing, and sigma uu will be equal to this thing here. It's equal to this. Actually, you can compute each of the element of this, because this will be an expectation of u1. Of course, I can write it this way because I know everything of zero mean. Otherwise, I need to write something like u1 minus mean of u1, u minus u1, something like that. And this is the mean. And because it's zero mean, I can just forget it. And expectation of u1, and u1 is equal to x1 plus v1. So I just have this one plus v1 square, and inside the term I have like x1 square plus v1 square plus 2x1 v1. But of course, if I take expectation of each of the terms here, expectation x1 square, I mean expectation is linear. I can take the expectation of this whole thing is equal to expectations the first term plus the expectation of the second terms and plus the expectation of the last term. And for the last term, it is because x1 v1 are independent, this will be equal to expectation x1 expectation v1 times 2. And of course this is zero mean, so both of them equal to 0, so this term is gone. Expectation of x1 is equal to 1, expectation of v1 is equal to m1, and we get that. So similarly, we can compute the others. We have this like that. And we can also compute sigma ux or sigma xu. Then each of this term here is, the first term will be just u1 x1, something like expectation of u1 multiplied by x1. In any case, we can compute all these matrices here. Then the conditional variance will be given by equation like that. I may have another video trying to derive this, but just take it for granted now. So this is basically saying that if you are looking at the estimate of x given you, the covariance of that estimate, it will be equal to the covariance of the original, the source or the original variable, that's the prior, minus this term here. We expect this is minus because now you have more information, then there should be like it's getting more precise of your estimate, therefore the covariance matrix should decrease. Kind of, not, I mean, of course these are matrices, so it's only a kind of Henry thing here. So we can substitute everything into this thing here. Then and also we can compute sigma uu inverse is equal to this. Now after computing this, we substitute the terms into here. We get this thing here, and again just some simple but a little bit tedious algebra. Eventually you will get that. So that means that the sigma x given u is given by that. And remember, the diagonal elements are actually just the variance of your estimate given your observations u. So therefore, like for the first variable, the distortion is just equal to this the first, the element here, so it's equal to this, and the second distortion of the second variable for x2 is just equal to this element here. Yeah. So then we compute the distortion in terms of m1 and m2. You'll see why we need that, but yeah, we just want to have that expression here. Now let's also compute the rate of ix1, the ix1 u1 given u2 and ix2 u2 given u1, because these are the bounds in the Bergerton inner bound there. For the first one, I can write this as hu1 given u2 minus hu1 given x1 u2, and because of the Markov chain that x1 x2 u1 u2 given if we consider variable u1 and given x1, then x2 we can ignore that, xv u2 we can ignore that, so we can remove this one here. So again, I just write down the variances for sigma u1 u2 because we want to do the same thing. We want to find the conditional variance. Of course, this is a little bit simpler than the last case because all the variables here is scalar. So we just compute sigma u1 u2, sigma u1 u2, u1 u1, and we got that is sigma u1 given u2 is equal to sigma u1 u1, or sigma u1 squared is 1 minus 1 plus m1 minus sigma u1 u2 is equal to this. Sigma u2 square is computed somewhere else, but it's equal to 1 plus m2. So this is 1 over sigma u2 squared, so it's 1 over 1 plus m2 times sigma u1 u2 and sigma u2 u1 get all square here. So anyway, we get eventually is equal to this. So therefore, not yet, we need to also compute sigma u1 given x1, but it's very simple. It eventually is equal to m1. Then finally, we can find the conditional mutual information is equal to 1/2 log this over that, this thing over this thing here. So therefore, it's equal to this. And similarly, we can find the other ru x2 u2 is equal to that. And both of them depends on m1 and m2 basically. And just to summarize, or actually before that, we can also compute u1 x1. It's very simple. It's equal to this, and u2 x2 is equal to that. We need that sometimes later on, actually almost immediately, so just include it here also. So this is a little bit a long story, but just to summarize at this moment that after kind of we introduce u1 u2 as x1 plus m1 and x2 plus m2, we can find that for Bergerton lower Bergerton inner bound, the distortion d1 d2 will be satisfied as long as the rate pair is within this range here. We have like something like a region, something like the R1 plus R2 is bigger than this term here. And R1, I think I can draw a little bit better. Let's see. R1 plus R2 is bigger than this. This is R1 plus R2 is bigger than equal to something. This something here. And I have this is R1, this is R2. and R1 is bigger than equal to this thing here, and R2 is bigger than equal to this thing here. For a particular chosen M1 and M2. And actually, if you change another M1 and M2, you should have something else, right? But what is interesting here is basically you always have this the bound for R1 plus R2 does not depend on M1 and M2, the choice of M1 and M2, but for the other, the bounds for R1 and R2, it depends on the choice of M1 and M2. So, as I said, like you can pick another M1 and M2. Maybe you will have some other region. Say, maybe I should use another color. Can I use another color? Maybe this can have another region, something like that, for example. Now, remember that like it's not really. I mean, this is getting close to the region that we defined at the beginning, the R1 D1 and R2 D2. But it's not the same because the region is something like that. We have the R1 D1 is basically we have R1 needs to be bigger than something like that. That is not a constant but depends on R2. And similarly, I have R2 D2 is a region that R2 is bigger than equal to a function of R1. And why so, basically? If we look at any particular chosen M1 and M2, we have an achievable region, something like that. Where, for example, I take an M1 and M2, any point inside a range like that will be achievable. Now, let's only focus on the corner points. This one here, let's say this one. This corner point is actually correspond to, okay, or like this corner point here. What's the weight for this? What's R1 and R2 at this corner point? Is for R1, of course, because it's 4 at this. I mean, it's kind of like what's the word? Adhere to the, or like it's touching the bound here. So therefore, R1 should be just equal to this thing here, right? It's equal to Ix1 U1 given U2 because of course this thing is R1 equal to or like this region is R1 bigger than equal to Ix1 U1 given U2. Let me get back to back. So therefore, this point here, just consider R1 is just Ix1 U1 given U2. And for this one, it turns out it's just equal to Ix2 U2. Why so? Because we can expand Ix1, X2, U1, U2 just using chain rule, expand in terms of U1 and U2. I have something like that. And then I expand again in terms of X1 and X2. I get basically 4 terms. But we find that 2 of the terms are actually equal to 0 because of the Markov chain here. So therefore, I have this thing, as you can see, like actually I'm expanding at this term here, this point here. But of course, by symmetry, I can expand at the other form here. I'm not sure I want to do it. Yeah, but yeah, just I will leave you if you're interested, like the watchers, as an exercise. By symmetry, of course, like we will have these 2 formulas. If you expand with another, basically, instead of u1, u2. Instead of writing u1, x1, x2, you have u2, x1, x2 plus I u1, x1, x2 given u2, then you will have the other form here. So anyway, then in any case, what we have here is the two corner points. We know what are the two corner points here. Is basically I x1 u1 given u2 and I x2 u2, and the other corner points I x1 u1, I x2 u2 given u1. Now if I consider, let's say, let's consider which corner point is better. Let's consider this corner point here. R1 is equal to I x1 u1, and we have computed that I x1 u1 is equal to 1/2 log 1 plus m1 over m1. So therefore it's equal to this, and from that m1 will be equal to 1 over 2 to the 2r1 minus 1. And u2 is equal to this, and also we computed that this one in terms of m1 and 2 is equal to this here, and we just copy it to here, and we can write this as something like this. Basically just multiply n2 times 1 plus m1 minus 4 square to both the numerator and denominator. Numerator and denominator. Then the first term here is just equal 1 over r d2. If you just look at earlier, we have compute the expectation of the distortion. This thing here, if it's touching the bound, this is just equal to d2, right? This thing is actually equal to d2. So, and this here, so this is equal to 1 over d2, and I have this here. I can substitute m1 now back to this equation here, and therefore I have something like that, and eventually I have this. So therefore this corner point is actually, I have r1 equal to this, r2 is actually equal to this here. And similarly, for the other corner point here, I will have r2 equal to this and r1 equal to that. And now we can really start showing that the weight pair inside the intersection of these three regions, R1, D1, R2, D2, and RS, D1, D2, is achievable. We'll start with the simpler case that this 1 minus D2 is less than equal to rho square 1 minus D1 is satisfied. When this is satisfied, then as we shown earlier on, that R1, D1 will be inside R2, D2, and RS, D1, D2. So therefore we can only consider points or weight pairs inside R1, D1. Now let's start with the corner points here. This the boundary R1, D1 intersects with the x-axis. Which, as we shown right at the beginning, this point here is actually have weight R1 is equal to 1/2 log 1 over D1. And we can achieve this point by picking n2 is equal to infinity and m1 to be something that such that okay, basically when we pick n2 is equal to infinity, that means that u2 can be anything, or that also means that like we're not sending anything for u2. Therefore, the weight for r2 is equal to x is equal to r0, and for the weight for x1 is equal to ru1 x1 given u2, and that is equal to 1/2 log 1 plus m1 over m1, as we can easily see earlier on. Let's see if we have that. Here. So for this one, if n2 goes to infinity, so this can be a global, square can be ignored, so I just have 1 plus m1 over m1 basically. And for this one, we want to target this weight to be 1/2 log 1 over d1, so that gives us like m1 is equal to d1 over 1 minus d1. So therefore we pick a choice, basically m1 is equal to this, and n2 equal to infinity. Now we need to show that for this particular choice, the distortion is in this is equal to is in this satisfy the constraint. So we compute distortion for the variable x1 is equal to this thing here that we computed earlier on. Now we substitute n2 to be infinity. We get m1 over 1 plus m1, and of course this is just equal to d1. And for the distortion of x2 is equal to this is equal to 1 plus m1 over 1 minus whole square over 1 plus m1. We substitute m1 here into this equation, and we get this here. So finally we get some the distortion is 1 minus whole square plus whole square d1, but this is less than equal to d2 because of the condition we have right at the beginning. So therefore we have, for this particular choice, the distortion is satisfied, and the weight required are corresponding 0 and also like log 1 1/2 log 1 over d1 as we want. So therefore this point is achievable. Now as we move upward, what we want is we want to pick some other m1 and m2. So let's pick now, because we're sending something for x2, we will have n2 tilde, the new n2 is no longer infinity, so we'll have n2 tilde, the new n2 is less than infinity, and m1 tilde will pick it in such a way that the distortion d1 is, the distortion for x1 is still d1. So the distortion for x1 is equal to this thing here, so therefore we want this to be equal to d1, so we'll have this, and we know d1 is just m1 over 1 plus m1, so we'll this equal to that. So what we see here is, you see this term and this term is the same, and we have this thing is positive. Therefore, like for this ratio equal to this ratio, we must have this m1 tilde to be larger than m1. So we have this here, m1 tilde larger than m1. So what we have is m1 tilde is a little bit bigger than the original m1, and m2 tilde is a bit smaller than the original m2. And for such choice, you have d is d1, the new distortion for x1 is the same as the original d1. Now for this distortion for x2, we can compute the ratio of distortion of x2 with the distortion of x1. That is equal to this over this, and that's, we can rewrite it this way. And the distortion of the original d2 over d1 is equal to this. And we can see that very easily that the ratio of distortion is smaller for the new distortion pairs are smaller than the original distortion pair, because like m1 tilde is smaller, so therefore this numerator is m1 tilde is bigger, I want to say, so therefore this numerator here is smaller than the numerator here, and also for n2 tilde is smaller, therefore this denominator is bigger than this denominator there here, so therefore this ratio is less than equal to this one. So, and this means that the new distortion d2 is smaller than the original d2, so therefore like, the distortion constraint is also satisfied. So for this particular choice of m1 tilde and m2 tilde, we will have some weight region, and with distortion will satisfy our constraint D1 and D2, we have basically some N1, N2, something like that probably. But what's going on is, for this particular wave region, for that choice of M1 tutor and M2 tutor, the left corner point will have rate equal to 1/2 log N2 tutor plus 1 over N2 tutor, and for x2, and the rate for x1, that's why as R1 tutor will be equal to 1/2 log 1 minus whole square plus whole square tutor, something like that. So that means that the left corner point actually is touching the boundary of this R1 D1 here. So therefore, like, if we decrease N2 and correspondingly increase N2 such that the distortion for x1 is satisfied, we will have the left corner point of the corresponding region is just trace on, just checking or like following along the path of the boundary of R1 D1. So therefore, any point on R1 D1 can be satisfied, on the boundary of R1 D1 can be satisfied, and of course, like, any point to the left of the boundary can be satisfied by simply padding rate for x1. So therefore, like, every point in the region of R1 D1 is satisfied. Therefore, the intersection of these three regions are also satisfied for this particular case. Okay, now let's consider the second case. That's when 1 minus D2 is bigger than rho square 1 minus D1. For that case, the intersection of the region R1 D1 and R2 D2 will kind of overlap. I should say overlap, but will not be inside the region of R1 RS D1 D2. So therefore, there's a tip that actually this the intersection here, it kind of a little bit get outside of the R1 RS D1 D2 region. So we will have something like this shape here, and we want to show that any point inside this intersection of these three regions can be achievable. And to do that, we first start with the corner point here. For this corner point, we will try to pick an M1 and M2 such that, let's say this corner point is R1C, R2C, such that I have this weight here is equal to R1C. I know that this is actually just equal to I U1 X1 given U2. And this, and also like 1/2 log 1 plus N2 over N2, this is actually is equal to I U2 X2. That thing we want it to be equal to R2C. And since this R2C is actually the intersection of the boundary of R1 D1 and also RS D1 D2, therefore it satisfies both equation that R1C is equal to this, and also R1C plus R2C is equal to this. And from that, and also quite a lot of tedious algebra, you can show that the distortion for x1 that's given by this one is actually equal to D1, and also a distortion for x2 is actually equal to D2 as what we want. So therefore, like, picking this M1 and N2, this point can be satisfied. Now, For this point, since it's achievable, then again, just like in the case 1, in the first case, we can try to show that the point on the boundary of R1 D1 here will also be satisfied. What we need to do is just we need to find some M1, M2, some new M1, M2, M1 tutor, M2 tutor, such that the combination of that is still equal to D1, so it's still equal to the original distortion for when we have like M1 and M2. So therefore I have this here. And given that using the similar argument as before, we can show that, as in the first case, we can show that the distortion, the corresponding distortion for this choice will be less than equal to D2. So therefore, like for that choice of M1 and M2, or the M1 tutor and M2 tutor, we will have the distortion is satisfied, this distortion constraint is satisfied. And also for that M1 tutor, M2 tutor, we know that the corner point for that choice actually just hit the, this is very hard to see, I guess. See if I can zoom it more. Yeah. For, let's say if I want to achieve this point, for my choice there, I basically will have the achievable Burger-Tone weight region, and also my corner point actually will overlap with this boundary of R1 D1 here. So therefore, like that point will be achievable because it's lying inside the Burger-Tone weight region for that M1 tutor, M2 tutor. And again, I can just keep changing this M1 tutor and M2 tutor. But as long as I change it in the sense that the distortion D1 is still satisfied, and my entire curve here can be satisfied. And similarly, on this other point, I can do I can find another M1 tutor and M2 tutor, but this time I'm not looking for the upper corner point, I'm looking into the lower corner point. And this, using the same argument, can be achievable. And then again, we will change the M1 tutor and M2 tutor, and we get some other Burger-Tone weight region. This is a little bit not very nice drawing, such that I want to say this. Let me okay, a little bit. So my R2 D2, so somewhere here. So by my same argument, this corner point first can be achievable, and then for any point on this R2 D2, I can find another M1 tutor, M2 tutor, such that the corner point of that M1 tutor, M2 tutor will overlap with this point here. That's basically the same point here. So therefore, this corner point is achievable as is inside the Burger-Tone weight region. And also, this point will have distortion equal to D2, and the distortion of x2 will be equal to D2, and the distortion for x1 this time will be less than D1, so therefore like satisfy the distortion constraint also. And using that, we can show that like every point along here can be achievable, and then like for points between these two can be achieved just by actually it is, of course, you know it's achievable because we start with the M1 and 2 such that this is covered by the Burger-Tone lower bound, Burger-Tone inner bound. But of course, you can also use the time sharing argument because this point is achievable, this point is achievable. You can time share these two schemes, use this scheme for so many times, use this and the scheme for some fraction of time, then you can achieve any points between them. And then everything like on the left will be achievable simply by padding the weight for R1. So okay, that's basically conclude our achievable part of the problem of distributed lossy distributed source coding problem with two Gaussian sources. Okay.